So this is for the Millikan experiment. Millikan wondered if all charge is, anytime you charge an object, if the charge on that object is a multiple of some basic number of charge. So I like to imagine, for example, well, on my slide, I think I have hot dog buns and hot dogs and stuff, but let's do eggs. Maybe that's an easier one. If I sent every student in the class to the store to buy eggs, you might come back with, I don't know, 12 eggs, or somebody might come back with 36 or 48 or 60, something like that. The reason you'd come back with those numbers is because all eggs are sold in 12s. I know there are some exceptions. I've seen like half dozens and stuff, but let's say for the most part, all eggs are sold in 12s. And so regardless of how many you came back with, it would always be some multiple of 12. Even if nobody came back with 12, if people came back with like 36, 48, 60, we would be looking at those numbers. Let's say this set of numbers here, we could say, well, if you come back with 48 eggs, maybe they're sold in 24s. But if that's true, then I couldn't come back with 60 or 36 or something like that, right? We're looking for, what is it, the lowest common denominator or least common multiple or something like that. Anyways, what we're looking for is kind of the largest number that they're all multiples of. Greatest common factor, maybe that's it. Anyways, so it could be 2, but if it was 2, we would expect to see something like 38, and we never see 38 eggs. Okay, so in my egg example, all eggs, if you go to the store to buy eggs, all eggs are a multiple of 12. Millikan wonders in his experiment, or what leads him up to this experiment, is he wonders, is all charge on objects some multiple? So we've got a charged object here. He happens to use oil drops in a set of parallel plates. It doesn't really matter that it's oil anyways, but he's got something here and it's charged, and he says, what's the charge on that? And if I put a different object with a different charge, what's the charge on that? And are they all, kind of like in this example over here, are they all multiples of some lowest basic number? Okay, so that's what he's trying to do. What he realizes when he sprays stuff in here, some of the oil drops maybe come in and they're negative, and gravity, force of gravity pulls it down. So does the electric force, because a negative charge is going to be attracted to those positive plate and repelled by that negative plate. They're just going to splatter on the bottom. He doesn't care about those guys. He cares about the positively charged ones because he's set it up with a negative plate on top, positive on the bottom. What he's interested to find out is, when is the electric force equal to the force of gravity? When he does this, some of the positively charged oil drops may have an electric force that's too big. They may go up and splatter on the top. Some of them may have a force of gravity that's too big. They fall down, splatter on the bottom. He doesn't care about those. So he kind of randomly gets these charged oil drops. Some splatter on the top, some splatter on the bottom. It's the ones that kind of levitate right in the middle. Because those forces are balanced, those are the ones that he looks at. Those are the ones that he cares about. What he kind of says with them then is, if the force up is equal to the force down, so if the electric force is equal to the force of gravity, then what he knows is this thing here, force of gravity, is just mass times 9.8. Electric force is QE. Remember, electric force is KQ1 Q2 over R squared. We have a Q1, we don't really have a Q2 because instead of just a single charge, we've got these parallel plates. So we also know that electric force is Q times this curly E, that's the electric field. And just as a quick reminder, remember, electric field is kind of going all the way across here. It's going from positive to negative. It's nice and constant and uniformly distributed. So he knows this stuff. Now we also know for parallel plates that E is delta V over R. Okay, hopefully you remember that anyways. If I make that replacement right there, I'm going to get Q delta V over R equals mg. We can rearrange that thing and get Q is, let's see, R is going to come up, so mgr, and that delta V comes down. We're going to get something like that. He knows G is 9.8. He knows R. R is just this plate separation, okay, R, kind of from center to center of plate. So he knows what R is. Delta V is just the voltage that he dials up on this voltage source. Okay, this is just a machine. You can just dial up whatever voltage you want. So he knows this, he knows this, he knows this. The one tricky thing he has to find is the mass of those oil drops. doesn't matter for our purposes. He's got a tricky way to find that out, but he finds the mass. What he really wants to do then is he wants to calculate the charge on the oil drop. Then he's going to spray in more oil drops, find out which ones levitate, find out their charges. Maybe he adjusts the voltage, sprays in more. He keeps kind of doing this over and over, and he keeps kind of building up this list. Remember going back to our egg example. He builds up a list of eggs in the egg example, but charges. He builds up a list of charges, and he's looking for the lowest number that can kind of satisfy it. He finds this number. This number he calls the elementary charge, and it is 1.9, it's 1.6 times 10 to the minus 19 coulombs. Okay, that number right there, the elementary charge, happens to be the charge on one proton or the charge on one electron. Okay, so that's the kind of magic number that he comes up with. Now we can use this. So why do we care about all this stuff? That's kind of history. This kind of calculation, we'll do some of those at some point, but why do we care about this? What this means is all charge on any object, the charge on an object is equal to the number of either excess protons or deficit of protons or electrons times the charge on that proton or electron. Okay, so we often talk about electrons because it's actually the electrons that you can remove from an object or add to an object. The protons just stay still, but it's kind of a syntax, or it just depends on how you want to talk about it. I forget, there's a word I'm looking for, but anyways, we usually talk about electrons, but you could talk about protons as well. In this case, we've got a deficit of electrons. Okay, so imagine there's an object. Typically, any atom that makes up this object, for every proton it has, it's got a kind of a complementary electron. Those two guys kind of cancel out, and there's no charge, it's neutral. But if I start removing these electrons, so let's say I remove one there, I remove another one, so I've got an unpaired proton, I remove another one and another one, and the number of electrons that I remove is this. It's a big number. In my example here, it's 5. If I've removed 5 electrons, then I can say 5 times the charge on one electron tells me the charge that I've removed. You could also say the charge of 5 times the charge on one proton will tell me the charge that's left over. So that's what we're doing in this example. We're doing it with this number, not 5. So the charge on this object is the number of electrons removed. Or you could say, because I've removed that many electrons, that's the number of unpaired protons, times the charge on one electron or one proton. Again, it's the same number. We multiply that and we're going to get at least approximately 1.3 times 10 to the minus 2 coulombs. And that is how we use this equation.